Hello everyone. This is the second chapter and we're going to talk about this work, power, energy, and work is here we're going to discuss. So a lot of time you might have heard this word work. What is work? Like you've been studying for 8 hours and you're saying to your parents that I've been working so hard, or you're working in your office and it's staying in your table and you're telling your boss that I've been working so hard, so diligently. But in the sense of physics, are you really working? Well, we have to understand this one. What is work, first of all? So, work is when we can say work is said to be done when a force is applied, when we are applying a force, and that produces displacement. Now, mind this things. Here, two vectors we are talking about. This first is force and then displacement. And the displacement producing, it has to be in the direction of force. Now, this is quite interesting because a lot of time we have seen that we are applying force and the displacement is producing somewhere else. We'll discuss about this in later. There are a lot of examples are coming, but we need to really understand this. This happens all the time. No, it's not happen all the time. So this definition is wrong. No, this definition is not wrong, but we have to go a little deep to understand this work. A best way to define work, and I would say the easiest way to define work is to say that work is a dot product of force and displacement. Now, what I'm saying over here is dot product. You might have read this one. In while studying the torque, you have seen this. The torque is a cross product of force and perpendicular distance from the line of action of force. This cross product you might have seen, and when you're removing the cross product you give RF sine theta. So in the case of vector, when we multiply two vector with the help of cross, then we give sine theta. And in the case of this, where two vectors is being multiplied with the help of dot, then we give cos theta. So best way to define work is it is a dot product of force and displacement. Now, this definition is quite easy because it doesn't make you to understand that the displacement is being produced in the direction of force. It is not necessary over here, but actually it makes quite a sense. And this expression actually makes this definition correct. Let's understand this, how this FD cos theta is coming. First of all, you have to understand one thing over here, that work is a scalar quantity. Okay, why it is a scalar quantity? Because it has no direction. It is correct to say it has no direction and it has the magnitude but no direction. Actually, the vector quantities are two type of things. When the vector quantity is entirely made up of a vector quantity, then we can say it is a vector. But here you can see this work is made up of two vector. And here also the torque is made up of two vector, but the torque is a vector quantity. Work is not a vector quantity because here the dot is playing a game over here. Okay, so whenever any quantity, any physical quantity, which is the dot product of the two vector quantity, it becomes a scalar quantity. It has no direction. Better to say that it has no components. Like you can take the example here. Suppose there's a box which is kept on the floor, and this floor is supposed smooth. There is no friction acting on it. Okay, now I'm applying a force over here like this. Okay, this force is making a certain angle with this horizontal line. Okay, and when I'm applying a force, this box is moving in this direction. Now you can understand that the box is supposed to move in this way, but it is moving in this direction. That means there has to be some force over here which is making the box to move in this direction. And what kind of force is this? It is the component of this force. So we can break this force into F cos theta. Now you know this, whenever angle is made over there, so we take the component of cos and then we take the component of sine. which is perpendicular to cosine component, f cos theta. Now you can see this f has been broken down into f cos theta and f sine theta. Now the box has started moving in this direction. Suppose the box moved further and moved over here. Okay, so here, from here to here it moved. Suppose the displacement it produced, it is small d. Now you can see the definition of the work and you can understand what it is saying. Here we applied the force, but the displacement produced in somewhere else direction. You're understanding this. So here actually this force is applying, which is displacing this box. So we can say the work is a force is said to be done when a force is applied on a body and produces a displacement in the same direction of force. So we get this over here. This is the force actually here it is applying. Okay, and this is the distance is being produced. Sorry, displacement is being produced when you are applying the force. Then actually we can write this work done is the product of force and displacement. Why we are taking this force? Because this force is not this force is not creating the displacement, but actually the component of this force is creating the displacement. So we can say the work is over here is ft cos theta. Okay, hope you understood this, why it is coming. And when we remove this cos theta in the term of physics, we give the dot product. Actually, it is a vector method, like your different method you might have studied in the mathematics, like algebra or trigonometry or arithmetic. Vector is a kind of mathematics also that we mostly use in physics to solve the problems. So you have understood this. The best way to define the work is to say the work is a dot product of force and displacement. So it defines the complete idea. Okay, now understand this. When we are pushing this boy is pushing this box forward, and you can see he is applying the force in this direction, and the displacement is also produced in the same direction. So what will happen over here? Here's the forces. Suppose the force is applying F and displacement produced, which is S. So here F, S. And you can see the both force and displacement in the same direction. That means they are parallel. And whenever two quantities are in the parallel direction, so angle will be 0. So cos 0 will take, and then work will be Fs. So it's simple as that. The work will be the product of force and displacement. Many times a student makes a mistake over here that they say that work is the product of force and displacement, which is completely wrong. Don't say this. It is only right when the force is being applied and it's producing displacement in the same direction. So you can say it is the product of force and displacement, but you have to mention this, that displacement is being produced in the same direction where the force is applied. Otherwise it will be wrong. We have seen this case that I have applied the force in this direction, but box is moving in this direction, so we have taken this component of the force in order to take the expression of the work. Let's understand the different idea of the work and different cases. Like this is the positive work done. Let's take the example. If I'll just let this ball go, then ball will go down. It will go down and strike the ground over here. So you can see the ball is actually attracted by a force. What is the force over here? It is the weight. And how the weight is acting? Because of the gravitational force. So the gravitational force is applied on the ball, and this gravity bringing ball down. Now when it will come from this place to this place, suppose is coming from here to here, so it will, suppose it will create a distance of h. So here the work will be, we know this, Fs or Ft cos theta. D is the displacement over here. Here you can see displacement is being produced, which is h, and the force applied, which is F. And you can see the force and the direction of displacement is both in the same direction. So here we can take this is cos 0, and this cos 0, we know the value cos 0 is 1, so it will be FH. This is the work done expression for this, and this is we call the positive work done. Whenever we apply a force, like you can take the example, this is a box, we are applying a force over here, and this box moved in the same direction like this, okay, and produce the displacement S. So the work done will be Fs. And because why Fs? Because it is producing cos theta will be 0. So this will be the product. So we can say whenever the work done is positive work done, so it is the algebraic product of force and displacement. But you have to mention again that the force, that the displacement has to be in the same direction where the force is being applied. So that is the idea of positive work done. Now let's check the idea of negative work done. What is negative work done? Let's try to find out the negative work done. Okay, this is the example we're going to take. Here's the example of negative work done. You might have seen this moving any vehicle. Then vehicle actually pushes back the ground with a certain force with the help of heels because of the friction, we can say. Okay, so the wheel basically push it back and it produces displacement in the same in this opposite direction. So you can understand this. Here the force is applied in this direction and displacement is produced in this direction. Or you can say, suppose someone, a boy is playing with a ball and then throwing the ball upward. Okay, and the ball is going upward like this. Now you have seen just he is not applying any force when the ball is at a certain height from this, but there is a force acting on the ball, which is gravitational force. Okay, this gravitational force acting downward and the displacement is produced upward. Now you can see the force is going in this direction and displacement is happening in this direction. Okay, and force is going in this direction, so angle between them is 180. In the same way, you can see over here, the force is applied in this direction and the displacement produced in this direction. So force applied in this direction, displacement produced in this direction, and the angle between them is 180. Okay, let's put these value in the expression we have found out. Okay, this is the Fs cos theta or Fd cos theta we write. So F is the force and S is the displacement we produced, and then cos 180. The value of cos 180 is -1. Now you can see it is Fs minus Fs. Work done is minus Fs. So we call this negative work done because the value is coming in negative. No, actually, we can say that the displacement is producing in just opposite direction where the force is being applied. Okay, what actually negative work done does in the most of the cases? It actually does, it slow down the speed of any vehicle. Means if it is moving with a certain velocity, it will start decreasing the velocity, and that's what we call negative work done. Let's take the example of we have understood the positive work done and then we have understood the negative work done. Now we're going to understand no work done. Well, there are a lot of cases where the no work done is we can say that it's no work done. The first case is when you don't apply the force is 0. When you're not applying the force, it is possible for a body to move. Yes, it is possible. There's a lot of examples are there where no force we apply but the body moves. Okay, and there is another case when there is no displacement. Let's first discuss with the case where there is no displacement. Suppose this is the wall and somebody is pushing this wall so hard but the wall is not moving at all. So if the wall is not moving, displacement is 0 though you applied the force. You applied a lot of muscular force on the wall, but the wall is not moving at all. So the work done over here will be Fs cos theta. Okay, the F will be 0. So entire expression will be 0. So we can say the work done in the last is 0. And that is what we call no work done. In this case, what was the case is when the displacement is 0. Displacement is 0 or no displacement. Let's take the another example. Like I said, it is possible that the displacement is producing, that the body is moving in a certain direction, and but no force is being applied. Yes, it happens in this space, mostly in the case of satellite. Suppose the satellite is moving away, or you take something in the space and you push it away from the, when there is no gravitational force is acting, so the body will continuously move with a constant velocity. Body going to move with a constant velocity. So this satellite will move in a constant velocity. The velocity will not change. Suppose the velocity over here, the initial velocity of the satellite at a certain time t is v, and after some time t dash, the velocity will, final velocity will remain same, which will be v. So you have seen that the velocity is constant, and when the velocity is constant, obviously it will produce something certain displacement. But when a velocity is constant, the force will be 0. How? Let's take the example. Force is actually equals to mass into acceleration, and we know acceleration is just a change in the velocity. It may increase or decrease. Okay, so it depends where the acceleration is acting. Now we have seen this case of satellite, or you just push something in a space, so the body keeps on moving with a constant velocity. Now this is the final velocity. Instead of final velocity, we'll write v, and instead of initial velocity, we will write also v. Okay, so this v minus v will be 0. And 0 upon t will be 0, and 0 multiplied 0. Now you can see this force is 0. Though the displacement is being produced, this satellite will move from this place to this place, but ultimately the displacement will produce, but the force is not acting. So here one conclusion we can draw over here. That's a very important thing to understand. It is possible to move a body without applying force. Yes, but in the case of constant, that has to be, speed has to be constant, the velocity has to be constant. So we can say, yeah, the body will move without applying the force. Okay, now what about the work? Now you are not applying any force. Now you have to understand this. So the force is 0, displacement is being produced in the same direction with the in the same direction. It is means it is going constantly in the same direction. So you can see over here the work will be 0. So another second case, we can say how the work can be a 0 when there is a no force is applied. This is the second case, no force applied. But it is possible that force is being applied and displacement also produced, but still work is 0. So you might be thinking, no, it is not possible. It is possible. It is possible in the case when the force and the displacement is perpendicular. When the force and displacement is perpendicular, then we can say work done is 0. Now put these expression into this expression of work. F and S cos 90 will be, we are writing instead of theta. Now cos 90 value we know is actually 0. So what will happen over here? It will be Fs cos 0. Now work done will be 0. So we can say this, whenever there is a force and displacement is being produced will be perpendicular to each other, then the work done will be 0. Now you might be thinking how it is possible. Okay, it is making some kind of illogical sense, but in the upcoming videos we will discuss about this, why it is happening, why we in the case of physics, we take these things, no work done. Okay, and there is a logical explanation also, and some kind of we can say logical also mathematical explanation for this. Let's understand this. This is a very good example why work is not being done. Sun revolves around the sorry Earth revolves around the sun. Okay, sun is also revolving in the somewhere Milky Ways and galaxies, we know this. Okay, now for this while, let's understand the sun is revolving around the Earth is revolving around the sun. Okay, when it is revolving around the sun, you can see there is a gravitational force that is acting on this Earth due to sun. And this gravitational force is towards the sun, is this way. And you can see this Earth is moving in an orbit, in a kind of elliptical path you can take, or you can say for this time the circular path. Okay, but actually the it is the elliptical path. So for some small distance, you can see for a very small distance when this Earth is moving, it is a straight line. Now you might be thinking how it is possible. Just take this example. Suppose we are making a big circle like this. This is not looking like a circle, but you can consider for some time. Okay, this is circle, and take a very small piece over here. It is not looking straight. And you might have heard this, you might have read this from your mathematics teacher that says the circle is made up of infinite straight lines. So you can say for a very small fraction of time, uh, Earth actually moves in a straight line. So when Earth is moving in a straight line and the force acting in this direction and very small displacement is produced in this direction, very small. So you can see here the 90-degree angle is formed. So we can say work will be work will be 0 Fs cos 90 degree, and this will be 0. Now this gives a great sense. Now think about this gigantic ball Earth is moving, and it is continuously moving. Now, if you want to move from one place to another place, you need to spend some energy or you need to spend some fuels. But think about it that any country or any one that is refilling the fuels of earth on the earth and making it to move, no, the earth is constantly moving and not taking any kind of energy. It is constantly moving around the sun. Why? Because it is not doing any work. When you are doing any work, you have to spend some energy. And then you can see Earth is not doing any work revolving around the sun. Then you can say it is not spending any energy, and we don't need any kind of machine or the fuel to move the Earth around the sun. And that is the beauty of the physics that explains the natural phenomena in a very explicit manner. Now you can see this is another example. You can take how electron revolves around the nucleus in the same way. Electron is revolving around the nucleus. You can see over here. Here gravitational force will act, but here a very strong force is there, which is we say electrostatic force. Okay, because the electron is negative and the proton is positive, which is in the nucleus. So proton attracts the electrons constantly, and the electrons revolves in this way. For a small fraction, for a very small fraction, this will be a straight line. Suppose it is moving in this direction, and here it will be 90 degree. Okay, so what will be the work over here? Again, Fs cos 90, and this will be 0. Okay, now you see the another example like a lot of teachers tells, and you will find in your book as well, that work done by a coolie, and comes out that the coolie is not doing any work. Okay, so let's take the example how coolie is not doing work. With the help of physics, we will understand this. Okay, now let's take this example. Suppose the coolie is carrying load, and the load basically the force, load, weight is going down, mg, and this he is moving in this direction, displacement s. Now it produces displacement perpendicular to the force. Now you can say the work done will be 0, because the force which is mg over here and displacement s, both of them making 90 degree with each other, and the work will be 0. Now you might say this, oh Cooley, you're not doing any work because I have read the physics, you have not read the physics, so I'm not going to give you any money. So that's certainly not a case. He might be start beating you. Uh, but in this case, you have to understand that the physics telling, okay, this is not the work. But you might be thinking, wait a second. If Cooley is not working, then how he's getting tired? Or for you can take the example by yourself, like you are carrying a load, you're holding for such a long time, and you are just standing on one place and you're not moving at all, then the work will be 0. So how is possible? Actually the case is over here is of force. Now you have seen over here, force are the two types. One is conservative, another is non-conservative. So when the Cooley applied the force upward, it was a force we call muscular force, and the muscular force is a non-conservative force. What is non-conservative force and what is conservative force? The non-conservative force, when you do the work with the help of non-conservative force, it never is stored in a form of energy. How? Let's take the example. Suppose there is a box. Okay. Now you applied the force, that you are applying a force which is a muscular force, which is comes in the case of non-conservative force, and the box moved in this direction. Okay. The box moved from this place to this place, and this is case of non-conservative. Now you can see when you left the box moving, then the box is not coming back in the same direction. That means no energy is being stored. But just understand this one. Just understand how you move the box. You move the box against the friction, and the friction is actually non-conservative in the nature. Okay, now you are moving the box upward. Now here you're not applying the force against the conservative force, which is friction in this case, but here you are applying a force against the conservative force, which is gravitation. Okay, gravitational force. Now when you kept the ball over here from this place A to B at a certain height, when you leave the ball or the box will fall down at the same place. Why? Because the ball contains the potential energy. When you do the work, it transforms into in any kind of form, mostly in the case of two mechanical energy, which is potential energy and kinetic energy. And when you leave this box, it will change into kinetic energy. So here you can see when you have done the work against the force of friction, which is non-conservative, and you took the box from A to B, then in order to bring the box back, again you have to apply the force from B to A. But here you don't have to do any work further. Just apply the force on the box against the gravitational force and take the box from A to B. Okay, and you can just left the box from there, leave it, and the box will fall down. So you've understood this, that the conservative force always converts the work done into a form of energy, or energy converts into the work in the case of conservative force only. But non-conservative force actually, yeah, it doesn't mean that it is completely denying the fact that the force is applied and it is creating work done, and but it is not changing into energy. Ultimately it will change into the energy, like when you are pushing the walls, you're applying muscular force, and the muscular force is basically a non-conservative force. But after some time, you see your body gets heat up. Okay, like rubbing the hands also, it gets heat up. Why? Because this work done, which is being done by the friction, which is non-conservative force, it is not changing into kinetic or potential, but changing into the heat, form of heat or some kind of other energies it changes. But the conservative force always changes either in the form of kinetic energy or in the form of potential energy. So you have to remember this, and this is very crucial to understand because it solves a lot of misconceptions, a lot of queries of the people. So you have understood this. Actually, he is working, but working the school is working with a force of a non-conservative force, which is work. Hope you understood this and you like the video. And if you like the video, please subscribe our channel.